How? That's a question of science. Kaithar in Tamil Nadu. Rows upon rows of wind turbines sprout up here like seedlings of a bumper crop. But this is no ordinary crop. Operated by the Center for Wind Energy Technology, this farm is growing the energy future of India. Experiments and findings here will help us move to an age where we will no longer depend on fossil fuels as a primary source of energy. Where the never-ending resource, wind, will be the key to clean and green energy. If the Center for Wind Energy Technology, or CWET, has anything to do with it, wind energy will have a big role in the coming years and decades.
In India, electricity generation is happening about 212 gigawatts today from all sources, and wind alone is about 19 gigawatts today is available. The potential is available at 50-meter level as per the official declaration, 49 gigawatts all over India.
Potentially, wind can steer India's energy fortunes in a big way. How can this be achieved? This answer lies in a more fundamental question. What is wind? We have all experienced the sensation of wind, either as a gentle breeze, a sudden gust, or the forceful push of stormy winds. And while we may not always be able to see it directly, it is felt and observed through its effects. Put simply, wind is the movement of air all around us. The next question is, what causes air to move? The short answer is differences in air pressure between two areas. You can do a simple experiment at home. Fill up a balloon. You'll feel that the confined air inside it has more pressure than the outside. When you release the air through the balloon's narrow opening, you will feel the strong gush of air rushing out to balance the pressures. The same thing happens on a much, much larger scale all over our planet and in our atmosphere. When the sun shines on the earth, it heats different parts differently. It hits the equator directly and heats it up more than the other regions. As this happens, the warmer, moist air rises up, creating a low-pressure area around the equator. Now, cooler air from other regions to the north and south rushes in to restore equilibrium. When this happens, wind is born. But this is just one factor leading to the birth of wind. The globe is affected by many different phenomena besides the sun's differential heating. The Earth's rotation and forces like evaporation and condensation contribute to unique wind patterns such as trade winds, the prevailing westerlies, and even India's lifeline, the monsoon winds. And that's not where the story of wind ends. Zoom in closer and you'll find more reasons for wind to blow, either gently or violently. Coastal areas are affected by winds generated by differences in land and sea breezes. Even geological formations like mountains, valleys, and flat plains affect how wind blows. Mountain ranges like the Himalayas block cold winds from the north, while the Western Ghats fence in the wind, making the region to its east extremely windy. By now it's clear, wind is born not just due to one or two physical phenomena, but a highly complex set of atmospheric, oceanic, and geological reasons. At its gentlest, Wind can erode solid rocks over centuries and millennia. At its strongest, it can rip through entire settlements in seconds, reaching stormy speeds that are faster than bullet trains. This immense power has had scientists in the last several decades asking, how can wind's energy be harnessed efficiently to generate electricity?
Wind is freely available, there is no cost for the fuel, and it need not be transported, and all the advantages are there. It is a green power, it will not emit any carbon emission. That is why wind energy is very attractive in a country like India, where we are depending on fossil fuels in a very, very great sense.
Helping India reduce its dependence on fossil fuels through wind is CWET. Its research facility is dedicated to developing wind technologies for the new age, including identifying the windiest parts of India in order to generate wind power. How do they do that? That's where the Wind Atlas comes in. Just like an ordinary atlas gives us a map of land masses, continents, countries and oceans, a wind atlas gives us a complete view of how winds blow in different parts of the globe. It tells us the critical information needed to generate wind power, that is, wind speed and wind direction. But mapping the changeable winds of India is no easy task. From supercomputing to field measurements, it requires every resource imaginable. CWET's first job was to enlist the help of world-renowned wind energy experts from the Danish institute RISO DTU. These experts developed computer programs that mapped wind flow across the entire globe. Indian scientists collaborated with them to understand how these global weather patterns could be applied across India. Together, they developed a mesoscale model for India. But what does mesoscale model mean?
What we call as mesoscale model is based on weather models, large-scale circulations on the atmosphere, on any country. So, India being a big country, India was divided into 11 different zones.
Indian and Danish scientists studied global weather models. They then computed the complex weather data using parallel and supercomputing. The data described wind flow at a height of 1 to 2 kilometers above the surface. But that still wasn't enough information needed to set up a wind power station. Most wind turbines in India are not as high as 1 to 2 kilometers. At lower heights, where they are set up, like 100 meters, wind can behave quite differently indeed. This meant that the purely digitally computed wind atlas was still incomplete. CWET scientists would have to venture out into the field to fine-tune the measurements for lower altitudes.
We always believe measurement is reality. So, the measured quantity is the benchmark. The digital representation is a indicative wind potential at any location.
In the last decade, teams like these have erected measurement masts at 640 stations across India. The masts reach a height of 120 meters and can be lowered or raised to measure wind at 50, 80 or 100 meters. Each measurement mast is fitted with sophisticated wind instruments.
This is the actual typical model of the meteorological mast. It's a scaled down model. The model which contains the different instruments at a different level, which contains anemometer. The anemometer which measures what is the wind speed existing at the particular location, and this is called wind van. which measure the wind direction, which direction the wind which is blowing. The other instruments also we have it. This is called the temperature sensor, which measure the what is the temperature at the particular location, and this will measure the atmospheric pressure. So all this data are being logged into the data logger. So in wind industry we need every 10 minutes average of the wind speed. So this every 10 minutes average of wind speed is being stored in this storage device.
The full-scale masts are erected whenever there is a possibility of setting up a wind farm to generate electricity.
We are standing at the field wind turbine test station. So now a wind mast is being installed. The mast which has different instruments, that wind anemometer, wind van, temperature sensor and pressure sensor. The data will be collected and it will be stored in the data logger. It will be analyzed at the office. This data will be used for verification of our wind atlas.
We have mast measurements up to 640 stations all over India, and these measurements typically runs for one continuous year and one covering all the seasons of the year. And these measurements give you the wind speed distribution in that height along with the direction distribution in the same place. And these two are essential for planning wind farm projects.
For any given test site, the mast collects data for 1 year over a 10-kilometer radius. All this data is then transmitted via GPRS to the head office in Chennai.
Google map which shows our Kaitar meteorological station mast, which is a 70-meter level, which has 5 levels of measurement. So each levels of measurement we can see here, this is actual real-time measurement, real-time data, that we can transfer real-time data from the site to our CVET office, our wind resource assessment unit. After that we can process the data.
Here, the massive meteorological information is computed to answer the question, how much wind energy will the selected site be able to generate? So, higher the wind speed, more the energy that can potentially be harnessed from a given site.
So now you give any latitude, longitude at any height, we will be able to give you the wind speed distribution and direction distribution, which are indicative anywhere in the India.
This information can be used readily by those who wish to set up wind farms. All they have to do is get their hands on the Indian Wind Atlas. Released in April 2010, the Indian Wind Atlas combines on-site measurements with digitally computed data to provide wind information for nearly 1,70,000 locations across India. It's given wind energy enthusiasts a clear idea of which regions are best to set up wind turbines.
Wind power distribution in India has been in the behind the Western Ghats, on the eastern side of the Western Ghats, the entire line, West Coast line. The states like Tamil Nadu, Andhra Pradesh, Karnataka, Maharashtra, Gujarat, Rajasthan, all of them have excellent wind potential, because the wind behind the mountain, when it passes through mountain passes, gets an accelerated wind speed. That is why most wind potential areas are eastern side of the Western Ghats, not on the coast side. And these are the states, since the wind flows through all along through Himalayas, there are some more packets of other states as well, which may need exploration, and that will also have wind potential.
India is looking at a future where wind farms like these will dot our windiest regions. CVET is developing and testing wind turbine technologies to do just that. What's the basic concept of a wind turbine? Wind turbines are windmills that generate electricity. Windmills are tall towers. At their hub are a series of blades that encounter the wind. the wind flows over the blades, causing them to lift and turn. The blades are connected to a drive shaft that turns an electric generator to produce electricity. Depending on the location and its wind flow, turbines are differently designed. How tall should a mast be? What is the ideal shape for the blades? What kind of electric generator should be installed? These are all questions that can be answered by studying the wind atlas for any given site.
The wind atlas provides you, after release in 2010 April, at any given latitude longitude at 50 meter and 80 meter levels, it gives you wind speed distribution and direction distribution at almost 1,74,000 locations all over India, which is indicative potential, we call it, because we always believe measurement is reality. So, the measured quantity is the benchmark. The digital representation is a indicative wind potential at any location.
Besides being clean and green, wind energy can be an effective power source for many remote parts of India that aren't connected to the national or state electricity grid. Since wind turbines come in a variety of sizes and designs, they can be used for different purposes: industrial, small businesses, and even in homes. And while there is an initial cost to set up turbines, once erected, the power is free and unlimited. But there is one major drawback. Even in regions which the Wind Atlas deems suitable for wind farms, wind is unpredictable and changeable. Some days may be extremely windy, giving you a lot of power, but other days may not see anything but a light breeze. How can the unreliable wind be harnessed regularly? To resolve this problem, there are many wind turbine designs being developed across the world and in India. At CWET, engineers are developing turbines and generators that are not just low cost, but you and I can install them on our rooftops, even if the wind speed is not as high as at Kayathar.
At Kayathar Wind Turbine Test and Research Station, Center for Wind Energy Technology is conducting various types of type testing of small aero generators, which facilities available in India. It's a unique facilities available in India. Small capacity wind machines which can run very small wind speed, that means even with a velocity of 4 meter per second, this can be installed in any household with the household meeting the requirements of household, that is up to 5 kilowatt, 3 kilowatt, 1 kilowatt.
The challenge for wind technology is clear: to develop low-cost wind power systems that can extract the maximum energy from wind. In the last few decades, long strides have been taken by global scientists. As a result, countries like the United States of America have come to depend heavily on wind energy to meet their power needs. India is also on the same path to reduce dependency on fossil fuels using wind.
In spite of the ever-increasing cost of engineering materials, because of the technological advancements and large-size wind turbines and large towers and so on, the cost of electricity has, per unit of electricity generated from wind has come down from, say, 30 cents to 3 cents in US, or 30 rupees to 3 rupees today in India. So, this is a phenomenal achievement which has been possible because of the innovation that is taking place in this sector.
In India, as in the rest of the world, the field of wind power and related technologies is a new and exciting one. Technological advances like developing the Indian Wind Atlas put the power of the wind in individual users' hands. For India's dreams of an energy-secure future, the winds of change are definitely blowing our way. If you'd like to share your feedback on today's program, please send your suggestions and comments to Vigyan Prasar, C24, Kutub Institutional Area, New Delhi 110016, or you can mail us at info@vigyanprasar.gov.in.
This is Karyamanikam Srinivasa Krishnan, the Indian physicist, teacher and leader. Jawaharlal Nehru, another great Indian, once said of him, "What is remarkable about Krishnan is not that he is a great scientist, but something much more. He is a perfect citizen, a whole man with an integrated personality." Join us as we trace the footsteps of K.S. Krishnan and explore the many facets of this extraordinary man. He rose to fame because of his collaboration with the Nobel laureate C.V. Raman. Many believe that he actually deserved to share the honor. He worked on a bewildering assortment of scientific areas ranging from the magnetic behavior of crystals to thermionics and solid-state physics. He was also an inspiring teacher and a key figure in the development of scientific institutions in India that are relevant even today. In this film, we journey through Krishnan's life, mapping his inspirations, his triumphs and failures, his genesis and his evolution, in an attempt to get a glimpse into the man who still stands tall in the world of science. Karyamanikam Srinivasa Krishnan was born in 1898 in a small town called Vattrap in Tamil Nadu. His early education was at the school in his village. Even at this stage, his mind was receptive to the wonders of science. He recalls the excitement he felt as a 13-year-old boy listening to his science teacher. Even though my teacher was not a professional scientist, he was good at explaining science in a clear and captivating fashion. He demonstrated many simple experiments for us and also encouraged us to do experiments ourselves. Once Krishnan had to write an essay on Archimedes' principle. Even at this age, Krishnan was not content just reproducing what he knew. For him, science needed to be active and alive. He experimented and devised an instrument to measure density, which he then wrote about. Later, he realized that he had unknowingly described an actual instrument called the Nicholas hydrometer. This perhaps was the start of a lifelong career devoted to independent thought and research. In 1914, Krishnan left for Madurai, where he studied at the American College. He proceeded to Chennai, then known as Madras, where he joined the Madras Christian College. He studied science here from 1916 to 1918. Quite early on, his unique abilities at science were spotted. He clearly stood head and shoulders above the other students. This was proved when Krishnan won the Aberdeen Prize for Physical Sciences in 1918. By 1918, Krishnan had completed his basic degree. He was almost immediately offered a position as demonstrator in the chemistry department. Krishnan's flair for teaching was evident here. He used to hold lunch hour sessions for his students, which was broadly an open house where anything scientific could be discussed in an informal, freewheeling fashion. Many students claim that they learnt more in these sessions than in their formal classes. Students from other colleges also used to come to MCC, especially for these sessions. In spite of the satisfaction Krishnan got from teaching, it was not enough. He was desperate to be doing pure research. He needed to figure out where he would go next. At that point, there was a fair amount of buzz surrounding the work of a young scientist called C.V. Raman, who was doing exciting research in the University College of Calcutta. Krishnan decided to apply for the MSc program there. Meanwhile, there was an opening in the Solar Observatory in Kodaikanal, and Krishnan was recommended for that post. The post was offered to Krishnan. However, due to some internal politics, the offer fell through. Soon enough, Krishnan received a letter announcing that he had been accepted for the MSc program in Calcutta. He decided to go there. This turn of circumstance was enough to change the face of Indian science. And so in 1920, the young Krishnan arrived in Calcutta. He writes about this most exciting chapter in his life. I relinquished the small job I had and decided to do research in physics and went to Professor C.V. Raman in Calcutta. But he did not agree for my starting research immediately. Only after learning various aspects of physics properly at the Calcutta University for 2 years was I able to join his research group. It was 1923 before Krishnan finally joined Raman's team at the Indian Association for the Cultivation of Sciences. He had a grueling schedule. He would complete an early morning walk by 6 a.m., which is when he reported in for work. A little background here on the work being done by C.V. Raman's team. It all started with the blue sea. Raman wondered what made it blue and started studying the scattering of light. Sunlight is white light. When this light hits atmospheric particles, blue scatters the most, which is why the sky appears blue. What of the water? Well, first people thought it was blue because of reflection. But then why were wells and ponds not blue? There had to be some other explanation. In search of this answer, Raman set up experiments from 1920 where he studied the results of passing light through different materials. By 1922, he had already published some of his findings. In 1923, K.R. Ramanathan, another of Raman's students, was working on an experiment on the scattering of light by water. He noticed something unusual. When sunlight, filtered through a violet glass, passed through the liquid, the scattered rays emerging contained certain rays not present in the incident beam. So if the incident light has a wavelength of, say, lambda 1, the emerging rays will have some light rays with a wavelength of lambda 2. Ramanathan termed this phenomenon as weak fluorescence. This is when K.S. Krishnan's contribution started. From 1925, for 3 whole years, he studied this phenomenon. He did experiments to observe the scattering of light in 65 different carefully purified liquids. Most of the early work in Calcutta was done by the visual observation of color rather than photography. This analysis of light was made further complicated because any impurity in the liquid could scatter the incident light and produce light in a new color. Through his work, Krishnan realized that the new radiation was partially polarized, unlike ordinary fluorescence, which is unpolarized. Let us clarify. Very simply, unpolarized light is in all directions, as opposed to polarized light, which is in a single direction. Raman and his team needed to come up with a theory to explain this. He suspected that this effect was due to an entirely new type of secondary radiation, quite distinct from the usual fluorescence. On February 27, 1928, Krishnan observed a definite faint greenish glow in pure glycerine and reported it. Raman set out to study this on the morning of February 28. Here is a way of understanding what Raman did. The violet light of the solar spectrum is isolated with a violet filter and passed through the liquid sample. Most of the light emerging from the liquid sample is the same color as the incident violet beam. However, they were able to show that some of the scattered light was a different color, which they could isolate by using a green filter placed between the observer and the sample. What helped them come to this understanding was the recent discovery of the Compton effect. Simply put, this said, when a high-energy photon hits a target, it releases the outer loosely bound electrons. The scattered radiation experiences a wavelength shift. Raman realized that what he was observing was the optical analog of the same effect. By the next day, February 29th, that year was a leap year, the announcement was out in the Associated Press about this path-breaking discovery. By March 8th, Raman had sent a note to Nature announcing his discovery along with a complete explanation. The discovery came to be known as the Raman effect. It won C.V. Raman India's first Nobel Prize for Physics. For Krishnan and his entire group, the next few days, weeks and months were periods of intense activity as they studied the various aspects of this new phenomenon. To understand the level of Krishnan's contribution, 9 out of the 12 papers that came out at that time were co-authored by him. It was a time of strenuous activity. But clearly the excitement overshadowed any exhaustion. In fact, Krishnan refers to those 5 years as a festive season in my science life. From understanding the new phenomenon, the focus moved onto its application as a tool to study various molecules, gases, liquids, and solids. The Raman effect has huge applications even today. These are Raman spectra. They work like patterns, and each substance has a unique pattern. So using the different patterns, we can actually identify different substances. This has huge applications. It can be used to effect in medicine to aid diagnosis. It can be used in forensics to detect explosives, pollutants, or narcotics. There has always been some controversy surrounding Raman winning the Nobel Prize. This is because some believed that it should have been shared by Krishnan. Raman refers to this himself in a letter of recommendation to the Vice-Chancellor of the Andhra University. If the Nobel Award for Physics made in 1930 had been for the work done in the year 1928 alone, instead of the entire work on the scattering of light done at Calcutta from 1921 onwards, Krishnan could justly have come in for the share of the prize. Krishnan himself always believed that Raman was fair to him. Arnold Sommerfeld visited Calcutta in 1928 during Krishnan's stay there. Sommerfeld was a German physicist who had pioneered work in atomic and quantum physics. His work was so outstanding that he had been nominated a record 81 times for the Nobel Prize. Krishnan attended the lectures he gave on modern developments in wave mechanics. After listening to the lectures, Krishnan helped Sommerfeld put together a book for publication by Calcutta University. He added original ideas and supplied new and elegant mathematical proofs to the work. Sommerfeld was so impressed that he wanted to publish the book under joint authorship. With his characteristic humility, Krishnan refused. A little bit now about the kind of man Krishnan was. He was deeply rooted in his culture. He loved Carnatic music and had a deep knowledge of Tamil and Sanskrit literature. He was a strong champion of science writing in the vernacular. He did a lot of science writing in Tamil. His love for literature was huge. The authors he read ranged from Plato to Sir Arthur Conan Doyle. He was also a great sports enthusiast and played tennis and football. Every day he would finish his work and rush down to the Maidan in Calcutta to watch the football matches played out there. He would cheer so loudly and enthusiastically that the other bystanders were amused and annoyed in turn. His sense of humor and verve for life is evident in his encounter with some Russians during a science conference. There was a lot of vodka being drunk, and one of the Russians told Krishnan that vodka should be drunk in one gulp and not sipped. Krishnan, who was a teetotaler, announced that he would teach them how to drink the Madras way, and downed a glass without his mouth touching the rim. Thankfully, he was not adversely affected by the alcohol. The next step in Krishnan's scientific journey was the move to the Department of Physics in Dhaka University, then headed by S.N. Bose, another stellar Indian scientist. He was delighted with the congenial atmosphere under Bose's leadership and set to work with fresh energy. Even though he was still bathed in the glory of the recent Nobel, Krishnan was not content to rest on his laurels. Instead, he shifted his focus to completely different areas of research. The magnetic properties of crystals in relation to their structure. His research work focused on measuring the magnetic anisotropy of different crystals. Let us figure out what magnetic anisotropy is before we proceed further. Take an object. Place it in a magnetic field. If the material is magnetically isotropic, it will not move. However, if the substance is magnetically anisotropic, it will move and align with its axis along one of the magnetic fields. So magnetic anisotropy is basically the directional dependence of the material's magnetic properties. Today, with state-of-the-art machinery, this kind of measurement may seem easy. But Krishnan in the 1920s needed to use every ounce of innovation to come up with a technique. And he did. He called it the critical torque method. It is useful to have a little background in the work of Michael Faraday before we go on to Krishnan's experiment. In the 1800s, Faraday had discovered that when you create a movement in a magnetic field, you could produce an electric current. He also showed that the faster the movement, the greater the current. The slower the movement, the lower the current. Now Krishnan used this knowledge creatively and simply. What did he do? To find the anisotropy, he hung a crystal at the end of a calibrated quartz fiber. When the magnetic field is switched on, the crystal will turn if the material is magnetically anisotropic. By measuring the angle of the turn, he was able to calculate the magnetic anisotropy of the substance. This was a creative idea. Linear measurements in this scale are very complex because the movement is quite tiny. However, circular movements are easier to see and measure. He used this method to do work on the anisotropic property of graphite. He used liquid hydrogen to change the temperature and tried to measure the anisotropy at different temperatures, especially low temperatures. He found that the anisotropy was changing at different temperatures. This was significant because it was the first low-temperature experiment in India. Scholars like Schoenberg in Cambridge were so inspired by his method that they started using the same methodology in their research work. Even now, Krishnan's sealing wax and string methods find direct use in the latest research on the field. Today, the knowledge gained from this research finds use in vital areas like petroleum prospecting. The research papers published by Krishnan and his colleagues from Dhaka University are considered to be the foundation stones of the modern fields of crystal magnetism and magnetochemistry. In 1933, Krishnan came back to Calcutta to take up the post of Mahendra Lal Sarkar, Professor of Physics in the Indian Association for the Cultivation of Science. This was a prestigious post. It was also important because it marked the start of Krishnan's role as an institution builder. Through his years here, he continued to study the magnetic properties of crystals in relation to their structure. For this work and for his work on the Raman effect, Krishnan won huge international recognition. In 1937, he was invited by Lord Rutherford to the Cavendish Laboratory, Cambridge, and by Sir William Lawrence Bragg to the Royal Institution, London, to give lectures. In 1940, at the relatively young age of 42, he was elected a Fellow of the Royal Society of London. The year was 1942. The World War was on. By 1941, the war in Japan had started, and Calcutta was thrown into turmoil. There seemed to be a danger of academic institutions being affected, even shut down. Faced with a situation like this, Krishnan accepted an offer of a professorship in Allahabad University. An interesting piece of trivia is that this department was set up by Meghnad Saha, another stalwart of Indian science. The Allahabad years proved that Krishnan was not just a great scientist, but also a wonderful teacher. Krishnan always told his students, physics means facing facts. He undertook various investigations with his students that covered a large range of topics, varying from the scattering of light, X-rays and electrons, and statistical thermodynamics to quantum theories and wave mechanics. A whole generation of scientists got inspiration from studying with Krishnan.